Okay, I'd like to start this lesson with a simple polynomial division. So please pause the video, carry out this division, and then come on back. Okay, so let's do this division, and we're just really checking on a process that we've carried out a few times now, but we need to be pretty comfortable with. So x minus 2 is called our divisor, and x cubed minus 4x squared plus 2 is called our dividend, and the result is our quotient, and the remainder is our remainder. Righto, so how do we go about it? Well, we divide x cubed by x to get x squared, and then run x squared through, distribute it through x minus 2, so it's x cubed minus 2x squared. And then we do a subtraction, and we just repeat this process right the way down. Negative 4x squared, we're subtracting negative 2x squared, so negatives everywhere. Be careful with that. It's minus 2x squared. Now we've got a minus 2x up here. I need to drag my 2 down. I've got minus 2x squared when I distribute, plus 4x. This looks a bit strange. This is now negative 4x, so it's 2 minus 4x. I'll write it in the other order, because I need to deal with my x term. So it looks to me like I've got negative 4 there. Negative 4x plus 8. I hope we agree. 2 minus 8 is negative 6. So to write this out in full, I would be saying that my dividend, x cubed minus 4x squared plus 2, is equal to my divisor, x minus 2, by my quotient, which is x squared minus 2x minus 4, plus my remainder, which is negative 6. So, righto, let's build in some terminology here. So build in some function notation, because we want to operate on this this polynomial division in a way that helps us out. So this guy here, the dividend, right, he's most often called px, right? P for polynomial, a polynomial in x, because that's what we're mostly dealing with. Okay, now often we're dividing by linear functions, right? So we're going to go with that as we develop this idea. So I'm writing it in general form, you understand, px equals x minus a, being the general form of a linear divisor. And right, so what's left here is my quotient, isn't it? So let's call it qx. And then if I'm dividing by a linear, if that's my divisor, then my remainder is going to be, well, my remainder can be in terms of x. So that would be my general expression here for my remainder, because my remainder can be a function of x. But when I'm dividing by a linear function, my remainder is going to be a constant. So I'm just going to write r here for my remainder. I'm going to write it neatly. There we go. All right. So here we have a an expression that sort of generalizes this idea of taking a polynomial and dividing by a linear, or admittedly a linear divisor, and ending up with a quotient. So if our polynomial is, in this case, is a cubic, so our quotient is a quadratic, because our divisors are linear. So it's our q is going to be always, our qx is going to have a degree 1 less than our px in this situation. Our r is always going to be a constant. Okay, so what if, just say that we're interested, and we are, when we often are, we're interested in the remainder, just the remainder. So we really just want to know what this value here is going to be, and we're not so fussed about going through this whole process in order to find what the remainder is. Now that just so happens is something that we care about when we're carrying out polynomial operations. We might want to know what the remainder is, and specifically we might want to know if a certain divisor is a factor of our dividend. So we might be searching to see if we've got a 0 here, right? Because if I've got a 0 remainder, then I've got a factor, and if I've got a factor, then I know I'm in business in terms of being able to find the 0 of the polynomial, or the root of the polynomial, the solution, if I'm trying to graph it, etc., etc. So my remainder is of great interest to me. So let's have a little look at this expression here and think about what we might be able to do in order to isolate this value of r. If I want to find out what r is, what could I do in here that might expose r? Is there something I could replace a with that would take care of, let's say, this expression here? Okay, so if I say go in here and if I let x equal a, say, then this expression here goes to 0. So 0 times whatever my qx is, doesn't matter. That whole thing will go to 0. I'll be left with just r. So if I rewrite my expression here now as p, all right, so I'm letting x equal a, so wherever I see x, in goes a. All right, I've got a minus a by q of a plus r. Okay, so this whole thing here dissolves, so I'm just left with p of a is equal to 0 plus r, or just r. So that's quite an elegant solution. That's quite an elegant outcome, isn't it? What it says is that my remainder will be the value of my polynomial when we substitute a in, which is the 0 of this divisor, my linear divisor x minus a. So in words, so this is the remainder theorem. This is what we've arrived at here. All right, that's it's a novel title for what we've just come up with. I guess it says what we've done, and that is we've found the remainder. So the remainder theorem states the remainder theorem. The remainder theorem, I feel like I need to underline this. Remainder theorem. So the remainder theorem states that when a polynomial px is divided by the linear expression x minus a, then the remainder will be p of a. Okay, that's quite a nice little statement. All right, it makes sense. We can sort of see how it works there. That right at x equal to a, well, we've got nothing left in here. We've just got our remainder. So p of a should be our remainder. That seems to make sense. Let's check it on what we've done up here. So let's do a check. So let's check. Right, let's check the remainder theorem. Let's see if this is a valid theorem. Check the remainder theorem on the example above. So the remainder theorem states that the remainder is just going to be PA when we divide by x minus a. So up here, my a is equal to 2. So P of 2 is equal to, now my px is this guy here. All right, this is px. This guy. Px is equal to that. So I have 2 cubed minus 4 times 2 squared. 4 times 2 squared. What else have I got? Plus 2. Plus 2. So that's equal to 8 minus, what's that, 16 plus 2. So negative 8 plus 2 is negative 6. That seems to match. So my remainder theorem seems to be working for us there. Same remainder. All good. Okay, stands to reason. Quite straightforward, quite simple, very powerful. Okay, so that's my remainder theorem. The associated factor theorem is a corollary of this, which says that if the remainder is equal to 0 for a value of a, so if PA is equal to 0, then x minus a must be a factor, and that's we're going to use that a lot over the next little while. Okay, so I want to just move away from that now for a second, and I want to go to I want to show you another way of carrying out a polynomial division that's twice as fast, heaps faster. It does the same job, only it must be said on linear divisors. So we have to be dividing by x minus a or some linear expression, which most of the time we are doing anyway with our work. So most of our division is by linear factors. We're looking to see whether a linear expression is a factor, or we're looking to see what the remainder is. So it's certainly a valid technique, and I'm going to show it to you now. It's called synthetic division, and it's really a shortcut. So we're going to look at synthetic. Let's have a look at synthetic division. Synthetic division. All right, let's see if you like what you see here. Synthetic division. Okay, so synthetic division is really just it's a shortcut of long division, really. All right, it's a shortcut. Now, a division shortcut, a polynomial division shortcut. So let's see how it works. Okay, so what we are doing is we essentially long division is what's called long division for a reason. It's quite a lengthy process. What this does is it cuts through a lot of the stuff that we don't write down a lot of the stuff that we do with long division. And for instance, we only look at the coefficients, because really that's all we're dealing with when we choose what we multiply by, etc. We are just trying to eliminate or match coefficients. So this synthetic division approach is really just concentrating on the coefficients, and just a reminder that it is only for linear divisors. So let's carry out this same division, but now we'll do it by synthetic. And so I'll pick this guy up and I'll copy it down. Okay, so we're going to use this same example, and this is how we go about it. What we do is I'm just going to show you, and then I'll get you to practice it. We take the zero of the divisor, right? So the zero, we say that the zero of the divisor is a. Okay, so if it's x minus 2, the 0 is a. It's called the 0 because it's the value of x that makes the divisor equal 0. So we refer to that quite often. You quite often hear what's the 0 of this expression? Well, it's the value that makes it 0. So we take the 0 and we set it up like so. So we take the 0, and then we're going to kind of do sort of like an upside down division mechanism here. And just inside here, we're setting it up like a long division, but I'm not going to write x cubed minus 4x squared plus 2. I'm just going to write the coefficients. All right, so 1x cubed minus 4x squared plus 2. So I'm just writing out the coefficients, and that's it. Okay, I'm just going to whack another line down here just to give it some structure. Now, the first thing we do is we just take this leading coefficient and we just rewrite it. We just rewrite it down here. So 1, that just gets rolled down, and then we have a process, and this is where the algorithm really kicks in. So we take this 1 and we multiply by 2, and we write the result right here, and then we add the -4 to the 2 to get -2. And now we repeat. So similar to long division is that we just got a repeating algorithm that we just roll through. -2, so now we do the -2 times 2, and we write the result here to -4, and then we add 2 plus -4 is -2. Now, this wasn't intentional, but I have actually made a mistake here, but it's actually a good mistake to make because it's going to highlight something to you that is a common error, believe it or not. So you might have even thought of this as I was writing this out. Now, hang on a sec, what about the x? How do we represent the x? Well, we've got to write the x coefficient down as well. So we've started with, this is my x cubed, this is my x squared. My x coefficient needs to be placed in there, and it's 0x, and 2 goes in here. So that's going to change some things here now. And it was all going wrong, I could tell, because I need, my last number is my remainder, and I know that I'm after -6. So let's go back. 1 drops straight down, multiply, place, add, multiply. So -2 times 2, -4, add these two numbers, 0 plus -4 is -4. -4 times 2 is -8. 2 minus 8 is -6. Okay, that is it. We're done. So that's what we did here in the long division. We have done in one line of working here. So what does it mean? It means that I've divided by x minus 2, and this is my quotient. So I've got here, this is my qx. This is my quotient right here. And what does it read? Well, it reads, this is, I've taken a, what have I taken? A cubic, and I've divided by a linear. So I have a quadratic here. So this is x squared. This is x. This is, here is my constant term, x to the naught, and this is my remainder. Okay, so it's x squared minus 2x minus 4 with a remainder of -6. Is that what we got up here? X squared minus 2x minus 4? It sure is. So we would, just as we did up before, we would say that therefore this is this x cubed minus 4x squared plus 2 is equal to x minus 2 by x squared minus 2x minus 4 minus 6. Okay, so we get, it's way quicker, way quicker. So what I'd like you to do, I'm going to put an example up now. I want you to try using this synthetic division. So I'll put it up. I'll ask you to pause the video, practice it, and then come back and check your answer. Okay, so I'd like us to do this example here. Use synthetic division to find the quotient and remainder when we've got this cubic divided by x minus 3. But first, so I'll encourage you to pause the video at this point and go and do this. But first, I'd like you to use the remainder theorem to find the remainder. And so then when you go through and do this synthetic division, you can check whether your remainder matches the remainder theorem. Just tie all this stuff together. So use the remainder theorem first, then use synthetic division, and then come back and see if we agree. Okay, so the remainder theorem will be, so I'm dividing by x minus 3, so that means that I'm after the polynomial value at x equal to 3, where this is a 0. So P3 is equal to twice, so I'm just substituting 3 in here for x, so I'm just doing a P3. Remember, this is my px here. So 2 times 3 cubed minus 10 times 3 squared plus 15 times 3 minus 14. So we got 3 cubes 27 times 2 is 54. 3 squared is 9 times 10 is 90. We're adding 15 threes, which is 45, and then we're subtracting 14. So I reckon we got 54 subtract 90. I think that's minus 36. Add 45, we're back in front by 9. Subtract 14, 9 minus 14 is -5. So the remainder theorem would suggest that my remainder upon division will be -5. So let's check now by carrying out this synthetic division. So how do we do it? Well, it's the 0 of x minus 3 that we're putting out the front of kind of an upside down long division sign, and then inside we are just placing the coefficients of my cubic. So it's 2x cubed minus 10x squared. I'm going to be careful not to miss any terms: cubed, squared, linear. I don't have any zeros to represent on this occasion. Another line down here just gives me a bit of structure, and I'm away. 2 comes down and just gets placed there. That starts my algorithm off. 2 times 3 is 6. 2 times 3 is 6, so the 6 goes in there. So it's multiplication, now addition. -10 plus 6, -4. now multiplication, minus 12, now addition, 15 minus 12 is 3, now multiplication, 3 3s are 9, now addition, minus 14 plus 9 is minus 5. There we have it. There's my remainder. My remainder theorem agrees. Okay, so we can write this out. I have a cubic. I will be left with here a quadratic. So 2x squared minus 4x plus 3. That's my quotient. That's my quotient. And my remainder is negative 5. My divisor was x minus 3. And I started with px. So px is x minus 3, 2x squared minus 4x plus 3 is my quotient. My remainder is negative 5, backed up by my remainder theorem over here. So really quick, isn't it? Really quick. So that's a nice method to use. You're going to get what you need a lot faster. Long division is great, and you'll still need to use it for any divisor that has a degree greater than 1. But most of the time we are dividing by, our divisor is linear. So we can use this. Okay, so a couple more examples here. Use synthetic division to find the remainder when dividing. Okay, so I'd like you to do the same here. I want you to pause and do this. But I want you to firstly find out what the remainder will be just by using the remainder theorem, and then carry out the synthetic division. Right, I'm going to talk this through, but if you've done the question, so this, you could just be racing through this at ×2 or whatever, just to check. Although, please make sure you're being thorough and you understand what you're doing. We're dividing, this is my dividend here. This is my dividend. And this guy here is my divisor. Now the 0 of my divisor is negative 2. So I am going to do two things with that. I'm going to find out what f of negative 2 is, and that's going to give me my remainder. So that'll give me 3 by negative 2 cubed, I'm straight into negative 8, plus 11 by negative 2 squared, which is 4, minus 7 times negative 2, and then subtract 19. So I've got negative 24, I'm adding 44 to that, I'm adding 14, subtracting 19, what am I left with? So I've got plus 20, plus 14, so I'm at 34, and I'm subtracting 19, so that looks like I'm about 15 on remainder. Let's now check it by using my synthetic division. My divisor, the 0 of my divisor is negative 2, so down it goes. Upside down division. 3x cubed, 11x squared, 7x minus 19. Let's see how quickly we can do this. As we do more and more of these, let's see how quick we can be. So the 3 drops straight into that position there. 3 times negative 2, negative 6. Now I add, 11 minus 6 is 5. 5 times negative 2 is negative 10. Now I add, 7 minus 10 is negative 3. Negative 2 times negative 3 is 6. And now I add negative 19 plus 6 is negative 13. That seems to conflict with this. Okay, error spotted. I didn't put a negative in here. So that's careless. I'll drop back and redo. Now, all right, so what needs to change here? The 3 comes down. 3 times 2 is negative 6. Right, 5 times negative 2 is negative 10. Negative 7 minus 10 is negative 17. Negative 17 times 2 is 34. Negative 19 plus 32 is 15. That's looking better. So I've taken a, so my divisor here, my quotient is 3x squared plus 5x minus 17 with a remainder of 15. A divisor of x plus 2, and so that's what my f of x equals. Okay, let's do the same with b. Just want to make a point here. Again, we're dividing by a linear, so it makes this synthetic division all good. But why is this so quick? Well, there's two things. We're dispensing with all the x's. We're just dealing with coefficients. But also look at what we're doing here. When we multiply back up, and we did similar things with long division, but when we got to here, we were doing subtractions, weren't we? And when we subtract, we're just not as good at subtraction as addition. It's just the way it is. Our brains are much better at addition. But also we don't have to, and with subtraction comes double negatives, many spots for not just taking longer, but making mistakes. So this is accurate and it's fast. So it's good. Let's check again with B. Let's please pause, do B, check with the remainder theorem what the remainder is, use synthetic division, see how you go. Okay, so I've got, I'm now checking f of 5. My zero, let's make the point here. My 0 is 5. So 5 goes in. 5's the crucial figure. I put it into my remainder theorem. I put it in, so I'll find f of 5, and that's going to give me my remainder. 4 times 125, that's 5 cubed, minus 3 times 5, plus 8. So 4 times 125, we're at 500, minus 15, plus 8. So that's 485, 493. That's a big remainder. All right, let's check whether our synthetic division agrees. Right, so let's be careful here. We've got 4x cubed, I've got 0x squared, I've got 3x, and I've got a constant of 8. Plant that one down, and let's go. So 4 gets thrown in here. 4 5s are 20. 4 5s are 20. Norton 20 is 20. 20 times 5 is 100. 3 and 100 is 103. 103 times 5 is 515. 8 and 515. I've done it again, haven't I? There's a negative 3 here. Why am I missing the negatives? My apologies. Okay, no excuses for that. 4 drops down, 20, Norton 20, 25 is 100, negative 3 plus 100 is 97. 97 5s, 500 minus 15, that's 485. 485 plus 8 is 493. So my quotient is 4x squared plus 20x plus 97 plus 493 is my remainder. My divisor was x minus 5, and f of x is my polynomial. Okay, I'd encourage you to have a go at this example too, but if you want to see how it plays out, by all means. We've got a polynomial here defined by a function of x equals. It's a cubic. We've got all the powers represented, all the terms represented, cubic, squared, linear term, and constant. Okay, use synthetic division to show that x minus 3 and x plus 2 are factors of the polynomial. How are they going to be factors? They'll be factors if the remainder is 0. So I'm going to firstly run x minus 3 through synthetic division. Now what's that? That's my 0 is 3. My 0 here is negative 2. Okay, so 3 is going to go through. I could use the remainder theorem to show. I could run it through now. Maybe 3 cubed is 24, so 3 cubed is 27, 54, plus 3 squared is 9, that's 63. Subtract 45 is 18, minus 18 is 0. We can see that works. Let's verify with synthetic. So it's the upside down long division, and I'm just bothering only with, and I'll get the signs right. Please put the negative in. Negative 18. Okay, these are just my coefficients. What do? I roll the 2 down here. 2 times 3, I add. 7 3s are 21, I add. 6 3s are 18. How quick was that? So my quotient is 2x squared plus 7x plus 6. All right, so that's my quotient. My remainder, this says my remainder equals 0, so therefore x minus 3 is a factor of f of x. And this is the factor theorem. Right? So the factor theorem says that if we can find a value of a that makes my polynomial at x equal to a equal to 0, then x minus a is a factor. So we found one, and we're going to do it again now. We're going to run x plus 2 through the resulting polynomial, which is 2x squared plus 7x plus 6. So we'll just go and we'll do that in a different color, shall we? Maybe this one. So we'll take these coefficients, 2, 7, and 6, and we'll run them along through with the 0 of -2, and we'll see what we get. 2 comes down. 2 times -2 is -4. 7 minus 4 is 3. 3 times -2 is -6. 6 plus 6 is 0. So again, remainder is 0. So the remainder is 0. So the remainder equals 0 when divided by x plus 2. Okay, so that means therefore x plus 2 is a factor of our polynomial function. Okay, so what are we left with? What's this 2, 3 mean? Well, that means that is 2x, because we had a quadratic here now and we're dividing by a linear, so our quotient is a linear function. What am I doing? 2x plus 3 remains. So therefore, what happened here? We started with 2x cubed plus x squared, 2x cubed plus x squared minus 15x plus x squared minus 15x minus 18. All right, we ran x minus 3 through it, and we discovered it was a factor. Then so it was equal to x minus 3 by 2x squared plus 7x plus 6, by 2x squared plus 7x plus 6, and then we divided that by x plus 2, so we went one better. We got x minus 3, we got x plus 2, and what was left over? 2x plus 3 with a remainder of 0, so it fully factorizes. And that's what we've got. Hence, fully factorize a polynomial. We have done it. So in this massive lesson that we've just had, we've learned a quicker way of carrying out division. We've looked at a remainder theorem that says that if you're dividing by x minus a, then just sub in a into the polynomial, and that'll give you the remainder. Now, if that remainder happens to be 0, well done, you've found a factor. And if you can find a few factors, you can factorize a cubic polynomial, which is what we've just done, and that's new. We haven't done that before. So what's next? I think it's exercise 3J for some more practice and some more fun with this stuff.